Annette and Peyton and Taylor, good morning.
Okay.
Yeah, your ability to control your audio is on the left side, down at the bottom, and it's way over to the left. I'm turning you all on, hopefully. And Annette, let me see if I can get you. Kevin?
Yes.
Hey, hi.
How's it going?
It's going. Yeah. A little lonely, but it's going. I miss you guys.
Yes.
And it's kind of taken me a bit to sort of figure all this stuff out.
Yeah.
And Emily, yay. Gina? Yeah, good. Kyle? Eileen? So just a heads up on this, we'll start in just a few minutes, is I'm going to go through quite a bit, I think, depending on, timing, of the antibiotic PowerPoint, sort of as if we were together in class. But as we go through this, what I want to do is help you fill out the study guide. I know these study guides are long and, really do take your time. And as we're wrapping up this semester, we just have the rest of this week and next week and then the final. So I thought I would dedicate our meeting today. Then I have set up a couple of meetings for next week, Monday and Tuesday, to wrap up antibiotics and to help you prepare for the final. What's going to be on the final, what you need to have for the final. It will be take home again. So it'll be very similar to our other, our last test. But everybody is doing great on the study guides. So that's good. And, grades have come up, even though maybe you have trouble with the exam. So let me look at the time. We've got about a minute. Before we actually get to the PowerPoint and the study guide on antibiotics, do you guys have any questions? About the class in general, about the final, whatever. About the final, as we go through this, I'll give you some heads up. So, any concerns you guys have had?
I haven't.
Okay. Is this pretty much the first time you guys have used Zoom? No, you've used Zoom? Are you using it for other classes?
I'm using it for my calc class as well.
Oh, calc? Ooh.
Yeah.
I would need something if I were taking calc. My goodness. And Crystal's here. Karen, yay. Hi, Karen.
Yeah, hi.
Okay, so I am going to go to something called share screen. So I will end up kind of in the upper right-hand corner, floating somewhere up above there. And what you will see is the PowerPoint for antibiotics. And so that's where we're going. And if I keep looking down, I can't show two screens. I can't show two screens at a time. So I can only show you the PowerPoint, and then I'll be referring to the study guide and helping you fill it out. So if you have a pen handy or something, that would be great. All right. So and I lost it. I have done something. Hold tight. I've done this before where it disappeared on me. You're all there.
I think you can click on the bottom where it shows the PowerPoint.
Ah, thank you. There we go. Whoop. Okay, now can you see the PowerPoint?
Yes.
All right, and what I need to do. Okay, so yeah, I had lost my bottom, so I couldn't see what to do. Alrighty, so principles of antimicrobial therapy, and basically this is chapter 10. And one of the reasons I really wanted to more physically share this with you is that one of the lab girls that helps with all the prep is in the nursing program. And she said when they got to pharmacology, it was really helpful to have had some of this material from micro. You know, so that's really partly why I'm doing it. So the definitions, all the definitions would seem to be about the same, but there are subtle differences. So I'm going to go to chemotherapeutic drugs, and this is number 3 on your study sheet, where you have to distinguish between these different terms. Chemotherapeutic drug, as you can see, is anything that we use to treat disease. And it's not necessarily an infectious disease. So you see there insulin, anti-cancer drugs, but of course also includes treating infectious disease. Antimicrobial is just a general term, drugs for treating any infection caused by a microbe. It might be a parasite, it might be a fungal drug. We most commonly think of it as treating bacteria. And then antibiotic. This is really key because I noticed when I was grading the papers of those of you who did do antibiotics and antibiotic resistance, that for this definition, some would go off to Google and look for something, and it doesn't really define antibiotic quite like microbiology does. So notice the key to this is it's a substance produced by microorganisms
Caitlin.
that in small amounts inhibit other microbes. And we've kind of discovered why microbes do this, because food sources are very slim in nature. And so microbes produce these antibiotics to ward off and kill other microbes so that they have that food source. So for them, antibiotics are a part of their life. And then it is true that what happens is that they take these naturally occurring antibiotics, which you're going to see a list in a minute, and they modify them. And I think somewhere I asked, why do they do that? Why do they take the antibiotic and change its chemistry a little bit? And basically, it's to make them more effective. We'll get to that, I'm sure. But notice they're more effective, long-lasting, and easier to administer. And then synthetics are just what somebody comes up with in the lab. Then it says more than half of all the antibiotics are semi-synthetics derived from Streptomyces. Streptomyces is a funny organism. It's like it's half bacteria and half fungal in nature. And I have some really nasty pictures later of that. So another way to look at antibiotics is whether they're bacteriostatic or bactericidal. And then are they broad spectrum or narrow spectrum? So I thought this was kind of a cute little presentation over on, I think it will be your right side, is bacteriostatic and bactericidal, or is it on your left? Anyway, and then we're going to look at the spectrum of action as well. So bacteriostatic, notice it's right in the center there, prevents the bacteria from multiplying. So you're going to get rid of some of the bacteria, but they're still there and they can come back. You would think that the best thing to do is bactericidal, and the cidal at the end means to kill. So that's killing off the bacteria. And that's a good thing in one way, but we're going to find out that giving people bactericidal drugs can have a side effect that's probably not so good. Broad spectrum, I'm going to move to this little picture. This narrow spectrum only gets one type or one group of bacteria. Maybe it's just gram positives. Maybe it's just Mycobacterium. Then broad spectrum, again, looking at that is going after many groups of bacteria. Now this chart is not in your textbook, but I thought it was kind of neat. As you look at it, which of those lines represents an antibiotic that is broad spectrum? Notice we're going from Mycobacterium, gram-negative, gram-positive, chlamydias, rickettsias. Which one do you see has the broadest spectrum?
The tetracyclines.
Yeah, tetracycline. Right, tetracycline. So how did it? So we get to these learning checks, and you know you can go back. Some of them I'll do with you, some not. But check if your mic's on if you want to be able to answer anything. Little history. Microbiologists love history. I don't know why. They always bring it up, I think, in almost every chapter. But notice this. It's not really, it seems like a terrible long time ago, but notice 100 years ago, 1 out of 3 children were expected to die of infectious disease. And so, be really honest with you, people had big families. They had 8 and 10 children because it was expected that several would end up dying. Also, lifelong debilitation from things like scarlet fever, diphtheria, which I've talked about in class, tuberculosis. All of these were really what parents feared greatly. So we go to this guy, and this is Paul Ehrlich. And so if you go to your study guide, you want to get something filled in, number 2 on there. And actually, let's take number 1 if you happen to have your study guide handy. It says, about when in our history did antibiotics begin to be available? They were not really commercially available until after World War II. We used them in World War II. but they weren't really available for the public. So for the normal population, it was really the 1940s that we really started to be able to use antibiotics. And we go to Paul Ehrlich, and he was really looking for something that would kill bacteria but leave our cells alone. And so he says he was looking for a magic bullet. Now his magic bullet would be one drug that you could give that would get rid of all bacteria, which as it turned out was not possible, but that was what he was looking for. And notice it says this drug would bind to receptors on the germs and kill them while ignoring your host cells. And we're going to get to a little bit more about specific toxicity and that. He also proposed the term chemotherapy. And again, a drug that would kill pathogens and leave little effect or no effect, would have little or no effect on the patient. He found some really nasty things that would kill bacteria, but unfortunately had very bad side effects. Arsenic was one that he used to treat syphilis, which in those days was extremely pathogenic. And then comes Alexander Fleming. So what I have for Alexander Fleming that I wrote down is he is considered to be the father of microbiology. And he was working in his lab. He was a physician, but he was especially a bacteriologist. And he was working in his lab, and he went on vacation. And so he put all his Staph aureus plates in the sink. He was going to wash them when he got back. And these plates were not like our plastic plates we use today. They're actually glass. And so when he came back, he noticed that all around the bacteria, there was a zone of clearing, as if something had killed off the bacteria. And he did some research and he found it was actually a mold, and it's called penicillium. And that was really the beginning of our discovery of antibiotics, and that was a true antibiotic in order to treat infection. Now, the thing about this was that the strain that he discovered was not very strong. It was not very useful. And he played around with it for a while, but he couldn't really get it to kill most bacteria, so he gave up on it. And it does say there he coined the term antibiotics. And I don't know where I got that, because your book actually says on page 4 of your study guide, this guy Salman Wakesman, that he was actually the one who coined the term antibiotic. I think this is kind of like the father of microbiology, and we found out, well, it could be Pasteur, it could be Koch, it could be Leeuwenhoek. So maybe he was using that term about the same time as Waxman. And there he is, father of modern antibiotics. And he did smoke. He smoked in his lab, which would be definitely frowned upon today. So then Florian Chain, they really were looking for a penicillin that would produce lots and lots, well, a penicillium that would produce lots and lots of penicillin that they could use in mass production. And the whole idea was to try and help people who had wounds in World War II. And they did come upon a penicillium that was actually growing on a grapefruit. that they found, and it was very effective. And so that's where mass production of penicillin occurred. So Florian chain really made possible mass production of penicillin. And then when the World War II was over, they began to make it available to the public. In fact, we tend to think penicillin was the first drug that was used to treat infection, but in fact it was sulfanilamide. So you see this guy, and I never pronounce his name right, Domag, but this fella came up with a sulfa drug, the first sulfa drug that was very effective in treating bacterial infections. He discovered that in 1932, but it really, really didn't get, again, much acceptance or use until the 1940s. So that's that guy. And I put this guy in, Lewis Thomas. Lewis Thomas was a physician who was treating patients in the 1930s, 40s, early 50s. And he's written several really neat books about biology and medicine. And what he said was doctors could now treat and could now cure disease. And this was astonishing for most of them. The thing was, up until the advent of the use of antibiotics, all doctors could do was hold a patient's hand, stay with them, stay with the family. There was aspirin, so you could give aspirin for headache. There were narcotics, so you could give basically heroin and codeine for pain. But as far as actually treating a disease, that wasn't possible. So that really, when antibiotics came on, that's the beginning of modern medicine as we really know it. And so as a question, are all antimicrobial drugs antibiotics? What do you think?
No.
No. Antibiotics are derived from they're derived naturally from usually a fungus or a bacterium. And we assume the father of antibiotics is who?
Alexander Fleming.
Yeah, Fleming, Alexander Fleming. Okay, so I think in your study guide, we've basically covered number 3, distinguishing between the two terms chemotherapeutic, antimicrobial, and antibiotic. And you'll find in the PowerPoint in the book that the term antimicrobial is used most often, unless it's actually a product of bacteria and fungi. So if you come down to number 6, as I say, if you're filling this out, which should save you a little bit of time, it says the greatest number of antibiotics are derived from the bacteria in the genera Streptomyces and Bacillus. And you guys are probably familiar with Bacillus because we use that in lab. Bacillus megaterium, Bacillus subtilis. Very nice antibiotic, but it's out there, it's ubiquitous in nature, and that has been our source of a number of antibiotics. And then notice, and the molds in the genera Penicillium and Cephalosporium. You've probably heard of Cephalosporin. And just a chart here to show you that there are a number of antibiotics that are derived from something out there in nature. It shows the Streptomyces, the fungi, gram-positive rods there. There's Bacillus subtilis right there, Bacitracin. And I'm sure you've had a cut or a scrape before and used Vaxitrace, and it's a topical antibiotic. And this term, on your exam, I really emphasize this, selective toxicity. So especially when we're talking about internal use, taking it by pill form, and in fact, even injecting into someone. It says it's an antimicrobial drug. It must harm the microbes without causing significant damage to the host. There may be some damage, but it shouldn't be, the typical thing for a physician is do no harm. So that's the idea here, to do no harm. And then if you come down here, some drugs like penicillin have a wide range of their use. It says between the toxic level where they can cause damage and the therapeutic dose, which successfully eliminates the pathogen from the body. So that's the goal. And I'm not sure if I asked this looking back down at your study guide, but what is the basis of selective toxicity? And it's actually the second statement here. The difference in structure or metabolism between the pathogen and the host. So for example, we do not have cell walls. We do not have, sorry, my cell phone of all things. Sorry about that. So we don't have cell walls and we don't have peptidoglycan. So it's marvelous. We can go after the peptidoglycan of bacteria, and that's not going to have any effect on it. Right, so there's something called the therapeutic index, and I don't think I actually specifically asked you this in your study guide, but again, it's the ratio of the dose of the drug that is toxic to humans compared to the dose that you can give a human without, and the dose you can give a human and actually get rid of the organism. So notice this, the drug with the highest therapeutic index has the widest margin of safety. So you notice if the therapeutic index is 10, then it's a safer choice. Looking at this, which of the following antibiotics would be the safest choice for a patient with no exceptional medical history? And you always do need to look at that. Drug A has a zone of inhibition. Well, what is that talking about? I guess, a month and a half ago, I gave you a virtual lab, and it was on the Kirby-Bauer test, which is kind of neat. You put little antibiotic discs on a plate of bacteria growing, and then you see how effective that antibiotic is. If it kills off the bacteria, you're going to have little clear zones around your discs. So this is showing a zone of inhibition of 30 millimeters versus 20 down here. And so actually this is quite more effective than this one. But notice this, the index of toxicity is 12 here, 1.2 here. So which drug would you choose to give your patients?
B.
B, yeah, B, right. All right. So looking at some of these, the modern term best describing the property of an antimicrobial that targets bacteria while leaving a little effect on humans is what? Well, it's selective toxicity. And that's where I had that. What is the basis of selective toxicity? You want the biggest difference you can find between who you're treating, the human in our case, or the dog or the cat, or if you're a veterinarian, and that bacterium. You want something that's really different. So it will select for the bacteria and leave our cells alone. And then this, I go after this on your exam. Why are there few antifungal, antiprotozoan, and antihelminthic drugs? So antihelminthic are worms, going back to several chapters ago. Why do you think that we really don't have that many?
It's hard to choose medications for those because they are so close to our own antibiotic codes. They're gonna be very similar to ourselves.
Yeah, well, if I'm hearing you, if I'm actually hearing you correctly, each one of those organisms, protozoans, fungi, and worms, are all eukaryotic, and we're eukaryotic. So we would have to find something specific about, for example, fungi, to kill off the fungi and leave our own cells protected. So it's been very difficult to find drugs that are effective there. And modes of action. I asked you this on your final to list the modes of action, because we tend to think of number one, from our chapter on cell structure. We discovered that bacteria have cell walls, and these cell walls have peptidoglycan. And again, we don't have peptidoglycan. So the first thing I think we tend to think of is, oh, all antibiotics, all antimicrobials target this cell wall. And in fact, that's not true. It's actually the second thing. Most of the antibiotics we have today inhibit protein synthesis, and we'll get to that. I don't know if you've looked at chapter 10, but at the very end of the chapter is big chart that has all the different groups of antibiotics, their modes of action, the names of different drugs. It's pretty exhaustive. We can actually disrupt the plasma membrane. We can go after metabolic pathways. And finally, pathogen recognition or attachment. So that's actually number 14 on your study guide. And actually, if you want to go up while we're up there on number 14, number 11, it says, why can we not use antibiotics to treat viruses? So they're also a problem. We don't have very many antiviral medications, and that's because they don't have cell structure. We can't target any of these things. They don't have cell walls. They don't make their own proteins. They don't have a plasma membrane. Yeah, they can grab one on the way out of a cell, but it's not really something that's useful. So here we are. This is just a diagram to show the different modes of action here. And in class, that would be nice and big on the screen. But again, if you look down here on key concepts, it says antimicrobial drugs target certain essential functions of the microbe. but must not interfere with essential functions of the host. That is selective toxicity. All right, so looking at cell wall synthesis, most commonly the antibacterial agent goes for that cross-link of the NAMs. So why was it so important for us to understand peptidoglycan structure? Because then it helps us understand how antibiotics work. And so the drugs that really go after this are what are called beta-lactam drugs, like penicillin and something called cephalosporins. And I just want you guys to know, I told yesterday the folks that came for that session yesterday that when I signed up for Zoom, I just got a personal account, which gives me 40 minutes. And so we're actually about a half an hour into it. Yesterday, they didn't cut us off, but I don't know if they'll do that to us today. But I plan on just covering this. We'll pick it up Monday and Tuesday. I am going to make some afternoon sessions. I don't know why I keep doing 10 o'clock in the morning, because not everybody can come in the morning. So I will make some afternoon sessions like 1:30 or 2. But the idea is to get through the antibiotic study guide and through some of this material. So the key to these beta-lactam drugs, and you see 2 of them here. Here's penicillin, and the key is this right here. It's called the beta-lactam ring. And all, I think 50 different penicillins that there are out there and cephalosporins have that beta-lactam ring. And so again, penicillin, and it prevents that cross-linking of the NAMs. Remember, the tetrapeptide comes down here from one NAM, the tetrapeptide from the other NAM, and then they either bond through the amino acids or there's a little bridge that forms. Well, what's the end result of that? Well, notice there, the cell wall is weakened. We tend to think the cell wall, you know, is a little bit like cellophane or something. It covers the cell's born, it has a cell wall, and that's it. And then the cell dies, and there you go. It's constantly refurbishing and its cell wall. As the cell grows, it's adding cell wall on. So it's not static. And if you can no longer build the cell wall, it gets weaker and weaker, and this is what happens, the cell lyses. And that's what you see over here, is the cell gets so weak that it basically blows up. The wall loses what we call integrity. And so here's something you might see on your final. Why are penicillin drugs more effective on gram-positive rather than gram-negative? And if you go back and you think about gram-positive cell wall structure, it has thick peptidoglycan, many layers of peptidoglycan. They rely on that for their, you know, protecting them against osmotic changes and so on. Gram-negatives have that skinny layer of peptidoglycan, and they actually use their outer membrane to block antibiotics from coming in. So that's why these drugs go after gram-positive and not gram-negative. And so what happens to the bacterial cell? It lyses. And then, you know, people, when they go to the doctor, sometimes the doctor will give a penicillin that you can take by mouth. And sometimes they say, okay, we're going to give you an injection. Penicillin G is injectable, goes right into the muscle and then into the bloodstream. This one, penicillin V, is oral, and most of your oral antibiotics come from that. Narrow spectrum of activity, narrow because it's basically the best for gram-positives. And then we have penicillinases, and I want to just get there. I did want to show you these several of these structures simply to underscore this beta-lactam ring here, and then oxacillin. Maybe some of you have taken that antibiotic. Ampicillin, oh my goodness, very popular drug, or has been, especially for little kids. Amoxicillin and ampicillin. Beta-lactam ring. So the question is, how do antibiotics defend themselves against these penicillin-based drugs? And one of the things is they've developed over time the ability to produce an enzyme that destroys the beta-lactam ring. So they've over time evolved what are called penicillinases or beta-lactamases. And that is what has made them resistant. And so notice here, there's that beta-lactam ring over here, and then you have the antibiotic. It breaks up the beta-lactam ring and the drug can't work. So going to page 5, we'll just take a couple of these questions and then we'll be done. I don't want to keep you more than about 40 minutes. So number 15 on page 5 says, why are beta-lactam drugs called beta-lactam? It's because of the beta-lactam ring. And then what is the mode of action of the beta-lactam ring? Well, it basically prevents the formation of the link between the NAM to the NAM in the peptidoglycan. Technically, what it does is it blocks the enzyme that makes that connection possible. So the connection between the NAM and the NAM cannot be made. Then all you have are NAGs and NAMs, and they start falling off. Those layers just start falling off. And then your poor bacterium, it ends up naked and breaks apart. For beta-lactam drugs, you can look that up, but ampicillin is pretty popular. Oxacillin, amoxicillin, I'm sure you can look that up. And then what part of the cell do the beta-lactam drugs target? Is the cell wall, and specifically the peptidoglycan. And actually, number 19 is basically the same as number 16, because it says, describe exactly how the beta-lactam drug works. It targets the NAM to NAM connection. So that is broken. Those NAGs and NAMs, which are sugars, those layers just fall off, and you end up with a very weak cell wall. And then what is the function of the penicillinase or the beta-lactamase? That's an exam question. When you see that, do pay some attention to that. Keep in mind, this is produced by the cell. And this is really critical. The antibiotic is not producing the penicillinase or the beta-lactamase. It's the cell. And so that's, the cell is defending itself against the penicillin. It produces this chemical, this enzyme, in fact. Notice the ASE there. That's an enzyme that breaks the beta-lactam ring, and the penicillin can no longer break up the peptidoglycan. Okay.
No.
Do you guys have any questions that, would you be able to make it on Monday at 10, or so that we can complete the study guide and go through some of the last of the worksheet there, well, of the PowerPoint?
Yes.
Okay. Well, if you can, I can help you get through this. And as I do that, Monday will be a little different than Tuesday. I know one of you asked me, are you going to do the same thing every day? Actually, no. So from here, I'll pick up and where we left off, I'll make a little note, and we'll make a valiant attempt on Monday and Tuesday to complete the study guide, to complete your as much of the PowerPoint. I'll go along a little bit more smartly, just trying to get the idea of the amount of time it takes. But as always, you guys, you can text me. How many of you have my cell phone number? I'll give it to you if you want to text me about the final, or about anything about the course, the final grade, all that stuff. My phone number is 928-580-8518. So, or you can email me. But basically, all you have left, if you've gotten in your virus study guide, all you have left is to watch the Dr. Gerba video. And the reason I gave you that little YouTube is I actually saw him speak at one of my conferences, and he just has a way of explaining, I guess, hygiene and public health in a way that I think is not boring, at least. And a few years ago, I did bring him to campus along with the U of A. We worked together, and we brought Dr. Gerber here. And it was very entertaining, I will say. In person, probably more so than the YouTube. But so, and then the antibiotic study guide. So as you have time to work on it, if you find stuff you don't know what I'm looking for, just make a note of it. And if you can come at one of the sessions, I'll keep putting up a couple more afternoon ones, so it'll make it a little easier. That's what we have for the rest of the semester. So anyone want to add anything? So, boy, you guys are great. We got Emily and Kyle and Annette and Taylor, Cindy, Gina, Kevin, Karen, Peyton, there you are. I can't see you. Diana, Ivan, yay, Eileen, Crystal. Thank you all for coming. I really appreciate it. And I hope it's been a help to you. Yay, nay. Okay, so I'll let you all go. I'll close out the meeting, and as I say, we'll get together again. And I'm still in the process of putting your final together. And then remember, I don't keep secrets very well, so I probably will end up doing some heavy duty sharing. So everybody have a great day.
You too.
You
Thank
too.
you. Bye-bye.
Bye.
Bye.
Thanks, Rob.